And enter your question at any time into the Q&A box you should see on your screen. Okay, our first presenter is from Brainchip. Anil Mankar is the co-founder and chief development officer at the company. He's got extensive industry experience, including previously at Western Digital, developing their PC core logic chipsets, as well as at Connexent and other positions in the industry as well. So Anil, go ahead and turn it over to you. You can turn your camera back on. Anil? Anil, your camera is off, and it seems your mic is off as well. Go ahead and click on the buttons to turn yourself back on.
Yes, it is on now.
I hear you. I don't see you yet, so click on the there we go. Okay, great.
Okay, thank you.
Controls are all yours.
Okay, thanks, Mike, for the introduction. Again, like Mike said, we work at Brainchip, and Brainchip basically allows you to design chips that can mimic brain, which is the neuromorphic technology. And its conventional wisdom is neuromorphic technology is required for the future, and we begin today. The future is now. And we do that by introducing a Akida neuromorphic processor, which is a technology that makes intelligent AI possible. So if you see, most of the IoT devices that are today connected are competing for bandwidth. They actually take the sensor data, send it to the cloud somewhere, or a local data center, or on a factory data set, and then they expect the data to be analyzed and get results back. That has issues about privacy and security. Also, there is no learning in that, and the latency problem that created by the bandwidth requirements are huge. Our solutions focus exactly solving on this problem by applying a neuromorphic principle to the solution. Before I get into that, a little bit about Brainchip. We are founded in 2013, and we have about 55 data science and hardware software engineers, more than 14 patents that are issued. And we actually funded our company through a publicly traded instrument on Australian Stock Exchange. And we also trade on over-the-counter things here. Our customers that we are engaged with are, some of them are early access customers who have been testing our technology, evaluating them. We are doing some proof of concept for developing some neural network that are optimized to run in neuromorphic solutions. And we also have licensed IPs on these 5 markets: automotive, consumer, healthcare, imaging, and transportation. We are based in Aliso Viejo, California right now, Southern California, with offices in India, France, and Perth, Australia. So what we are introducing today is actually a first neuromorphic SoC, NSOC that we call it, on in a first to market that's commercially available. This takes advantage of best of both worlds. It runs as CNN that you can convert into what we call a deep learning SNN or a native SNN on the same hardware platform. So what happens is you get best of both worlds, the feature extraction of CNNs. They are well known for doing very good feature extraction. We maintain those. Also low power implementation of SNN. So we support that by actually having our own software development environment called MetaTF that actually takes your CNN and will convert them into event domain. Because we run both CNN and of course SNN in a neuromorphic event domain, we can actually have a learning available for both deep learning SNN, which are conversion from CNN, and native SNN. So with those solutions, we actually make edge AI analytic possible on the device because of neuromorphic nature and learning that we have. So what are the design principles that are used in Akida technology? One thing is, of course, it mimics our brain, so it does have distributed computation. That means what we have is a neural processing unit that actually has its own memory, dedicated memory and computation engine, which reduces data movement during computation. Similar to our brain has its own synapses and memory is stored in synapses, and each neuron can do the computation and learning by itself. Second thing is what we do is since we do only event-based processing, even in an activation map, when there are no events, we don't need to do any computation, and that reduces the total number of computation required for running an inference for a CNN. And also we allow the events to be multi-bit valued so we can maintain the accuracy of the inference. And all of this NPUs only have to perform on the events that are present in either weights or in activation map. And you don't have to look at complete activation maps. So that reduces the number of operations. So also, all the events that are calculated within the NPUs from one layer go to the next layer with the on-chip mesh that doesn't need any CPU intervention. And the actual network that you're running on our hardware, is configurable on the hardware on the fly through a runtime software that configures the NPU, programs them, programs all the thresholds and everything for the neurons, and it will do inference for the network that you are trying to run on the device. And also, because we are running the inference in event domain, we implemented a proprietary algorithm that is similar to static timing dependent plasticity. So we can run one-shot learning on the device. You don't have to go back to the cloud, and they can be continuous learning both for CNN that are converted into neuromorphic domain and also native SNNs. So that happens through our software framework that's called MetaTF. Meta means post. After TensorFlow network, we have the light blue solutions are what are standard TensorFlow functions. So you design your CNN in TensorFlow, you can train it in TensorFlow. After that, you actually use our dark blue solutions for quantization of a training. You can quantize because we can go down to 4 bits, 2 bits or 1 bit. You can retrain the network with the quantization of a training, fine-tune it to optimize the sparsity and other things, and then save the network in a TensorFlow format. Our runtime software now takes that network, programs all the NPUs, and it will start taking samples coming in and analyze the data, and also has learning on the chip. So this actually takes all the complexities of neuromorphic processing, how the neuromorphic processes are programmed and all that, and it makes it very easy and it's intuitive flow that can take either your CNN, your data set, you don't have to modify them to make it run on the IoT device. You can keep your data set, keep your network, go through the flow, save it in an Akida format, and it will run and get you advantage of low power, low amount of memory required, and also get a benefit of on-chip learning. How we do on-chip learning is actually, this is explained on this slide. Typically when CNNs are very good at extracting feature, like a MobileNet V1 that can extract 1,000 object classification, all of those features are extracted. So we maintain those initial layers, which does the feature extraction. And now we replace the last layer with a fully connected layer. That is, the classification is actually nothing but combination of the features at the last layer. Now, because when a frame is presented or any data is presented in front of the network, what is happening through the earlier layers are spike trains coming in, and that spike train actually allows the fully connected neuron to learn from a repeating pattern with just 1 or 2 shots. This is, of course, available for CNN that are converted into deep learning SNN. Similarly, for a native SNN, also the neurons will learn directly from incoming spikes by integrating the spatial-temporal nature of the information that is in incoming spikes. There are a lot of examples that we have on our YouTube channel. You can click on that to see that we can actually add objects on the fly. Google speech command network, once running on our device, you can add a couple of more commands to that, or learn directly from DVS camera for a hand gesture. So this is basically the technology that allows you to run CNN into neuromorphic domain and have learning. So one of the examples of one-shot learning could be that if you have a fruit classification on a conveyor belt and you were actually doing a orange and banana, you can actually add another couple of categories of banana on the device itself, like a green banana or a spoiled banana, and add that on a device. You don't have to go back. You don't have to have multiple samples of the new objects that you are adding. So that's one of the applications that you can do. Here's the chip that you see that's being available commercially now. It has a PCIe or USB interface coming in. It does have I2S, an interface for audio sample, I3C for sensor data coming in. We actually have implemented this in 28 nanometer that has 20 nodes, 8 megabytes of memory, and it has an on-chip pixel to spike converter or an audio sample spike converter. So when the data comes in, that is not really in the form of events. We actually do that on-chip conversion. Then we also have a LPDDR for this chip that can actually store external weights that may not fit on the 20 nodes. And if your network does not run on 20 nodes, and it needs larger number of nodes, it could actually either you can have multiple of those chips connected to a chip-to-chip expansion interface, or you can run the same chip in multipass mode and save intermediate results. We have a chip implementation, but our main business focus is licensing IP. And this is configurable nodes. We can start from 2 nodes to 256 nodes. Each of the node, 4 of the NPUs become 1 node, and they are connected internally through a smaller network. And each of the node has a second layer mesh network that communicate between the nodes. The system interface is basically AXI bus or any other bus, and that has built-in DMA for either configuration or, of course, for samples also. So no CPU is required even for configuration for this. We, of course, have an event conversion complex that also DMA-based that picks up events from system memory, convert them into either events coming in or data gets converted into events, passes on to the mesh network, and the results of that are passed on to the system again for after analysis. And the network size is basically customizable. How many nodes you need, that depends on our customers work with our Meta TF, decide what type of networks are required for the edge IoT device. Then with that data, they can decide how many nodes needs to be licensed. This technology is completely independent of process technology. It's all standard cell and SRAM. So we are process agnostic. You can implement that in 7 nanometer, 14 nanometer. We implement that in 28 nanometer initially for proof of concept and all the verification of the IP. This is now available. So we have 2 systems that you can order online, and we have a mini PCIe board with a chip on it that can plug in either into a Raspberry Pi system and accelerate and run networks on that, or a PC Linux box, and that is available now commercially. The chip is released to production, and we're taking pre-orders. So what does all that technology allow you to do? So, and how does neuromorphic computation applied to CNN actually benefit? So here's an example of standard keyword spotting that we took. We actually took the same, if we converted that network, this is the size of network, convert to 4-bit weights and 4-bit activation, and compare that with 2 implementation industry standard, Google Core TPU that does 8-bit integer inference, and NVIDIA Jetson that does 16-bit floating point inference. If you look at batch size of 1, this is the result we get. So if you can see, either you can look at IPS per watt or a microjoule per inference, which is low is better. And we can run the Akida either at 300 megahertz or 100 megahertz, or linearly go down almost to 5 megahertz and reduce microjoule per inference. While we compare the same thing with Coral development board that actually requires about 351 microjoule per inference, while Akida can go up to 83, and if you go down to 5 megahertz, then it goes into 40 microwatts for inference per inference. Similarly, Jetson Nano, we did 2 examples. One was standard Jetson Nano that gets you about 1,000 frame per second per watt in a 926 microjoule. And there's a node for which says don't spend more than 5 watts. Then it gets you about lower microjoule per inference and low power. So that's the advantage of standard CNN. Take the data set, convert it to our meta TF and run it on neuromorphic domain. Another example that we have is the tactile data capture. This data set is actually a 10 by 10 array where you can write your digits on it. There's a data set that's collected where 23 participants wrote with a pen. And now the samples that we got from them, one for on event, -1 for off event, and 0 for no events. We collected that data, which are spikes directly coming from the sensor. This is the pattern of spikes that you see. And when you do that, you can either take a standard CNN, so you can actually encode that data into basically all the events that happen at one place. You can run it on sum them up, and that represented as blue here. And red is where there's a negative event sum, and yellow is where there's no. So you could encode it as a CNN. Take a small CNN, which takes about 862K parameters, 4-bit weight, 4-bit activation. You can extract features. You get about 95% accuracy on that, and use 4 NPUs. Now you can run this at different speeds. At 5 megahertz, you'll get about 9 frames per second, and you'll spend 4.5 milliwatts for doing an inference and detecting a digit. While the same data set, you could either directly encode it into a native SNN. You can make it 2 channel, one for on events and one for off events. This takes only 1 NPU, but now it's a fully connected layer that is learning to detect the digits from directly events coming in. And at the same 5 megahertz, you get 66 frames per second, and the power is 1.8 milliwatts only. So same data set can either be coded as a native SNN or a CNN way. Of course, native SNN gives you much higher performance and lower power. So this is almost an order of magnitude. You get 7 times better frame per second and 1/3 the power. So that's a pretty good example. I have actually a demo that I can show you. Let me share my screen. I'm assuming you guys are seeing the screen. So if I play this, so this is the same, both the networks I run on our chip, and this is a digit 0 that's detected. Let me keep running it. So both of them, CNN and SNN, the power numbers are same, but this is actually running on the chip. We are showing results of, and you see on the right side, the dark numbers that you see, that means there are more events there. That is digit 9 detected by both. Of course, SNN is low power and higher performance, and this is actually running on our chip. So you can actually, this is real sensor data that's directly generating events, and those can be processed directly either CNN way or SNN way. I will, so that this continues, I'll go back to stop sharing. So that was the demo that we showed for digit detection. So what we have done is we have taken the technology and taken standard models like classification, person detection, all of those, and we have a model zoo that takes the standard face detection, classification, other object detection. Multiple networks are developed. We actually convert them, and it's available in our model zoo. You can download them directly, and they will run on the system that we are supplying. Of course, we have examples of devious cameras doing gesture recognition and all that, and those are all available. The neuromorphic computation actually allows you to do take advantage of sparsity in the data. We are working on some LiDAR implementations to really see how we can improve that better. So our business model is, our main focus is licensing IP for multiple vertical markets that we have. We of course have a chip that proves that all the IP is working. There's a one-stop shop. You can actually run any network, complete software, runtime, and runs on the platform. And then this is used for for evaluating how many nodes you should really do for a license for your IP. This is available now. So what we are trying to do is we want to make every sensor smart. That means that there is no reason that the sensor data has to go to the cloud. And look at how many IoTs are there in the world. And each IoT can become an AIoT that does analysis. Now we actually make the sensor smart and actually make it simple also. So the fact that it's neuromorphic, it takes advantage of low power, low memory, everything else, but it's also simple to use through our software flow. And we want to save time in terms of taking your networks, deploying them in the field. There are a lot of networks available today. People are struggling that it doesn't fit into the IoT device they're trying to do. They have to go through tune the network, reduce the weights, change the network, again go back to the cloud. So we are saving your time. We don't want to waste your time. We actually save it. And we are actually trying to solve a tough edge AI problem that probably other people cannot solve, because we actually, typical use case model is you actually have some learning to be done. You want some simple object that you don't have multiple, you don't have access to the cloud. All of those things can be done. And actually your edge IoT device can really have intelligence built into that and make it very easy to deploy. So that was my last slide, I think. Yes. So we want to bring intelligent AI everywhere, and that is our mission. Mike, maybe we can take questions.
Thank you, Anil. It's another interesting presentation. I think I learned something new about your architecture every time I see this. We have some questions coming in. Please go ahead and enter more questions. We'll have time to go through several. I have some to start off with. Well, first of all, with your software, your runtime, does Facebook know that you're joining the metaverse?
Well, we thought of meta means post, right? So we actually, and we want to say something about TensorFlow. I don't know about what Facebook is trying to say, but meta TF is basically post TensorFlow. That's the message. Yeah. You are happy with your TensorFlow care, and you can do all the tricks in your TensorFlow, by the way, with whatever network you're optimizing TensorFlow, do that. But once you use MetaTF and you come into our neuromorphic domain, you don't have to go back to the cloud.
Yeah. Your tactile sensor example is a good demonstration of the power savings of using a spiking neural network, inherent sparsity, spatial and temporal sparsity as well. How could you give an example of how do you convert an image to event? So what would be an event?
Okay, right. So image to the event, of course, DVS cameras give you events directly, or even the tactile sensors giving events. We actually take like a full HD image, let's say 2 million pixels. We actually run the first layer, which is typically a convolution layer with RGB data, and the convolution, which can be 3 by 3, 5 by 5. The output of the convolution is where we apply some thresholding logic to say, is this a event or not an event? So we actually are converting to a thresholding and a small algorithm that we have that takes frames. And then if you see where the object is in the frame, then you'll see that the intensity and RGB values are different. That's why you could actually see different event, different spikes will come. So it's really a standard convolution on RGB values, and then having a thresholding logic in our hardware converter that creates events, and that's programmable depending on the application.
Okay, and so if you have a 1-bit or a 4-bit event, would that in this case be indicative of the luminance relative brightness, or what would that indicate?
Yeah, so actually what happened, the 4-bit is, see, typically spiking neural networks in the event domain are 1-bit, right? So initially we took ImageNet and things like that and converted it to 1-bit. And of course, you're losing too much information. Most of the networks like MobileNet, V1, and other things are trained in 32-bit and inference is 8-bit. There's still enough information for accuracy. So 1-bit, you lose a lot of information. The fact that we are doing the computation in the event domain doesn't really do anything to accuracy. We're actually doing the same thing. But the fact that we went down to 1-bit, you might get only a 10% accuracy for MobileNet. So we kept on increasing the number of bits. So we're preserving the value that we get out of the activation map and map it to a total 16-bit values, and we can grade it that way. So we preserve some information. And we have a lot of data that says what the accuracy, and all of those things you can try it with our MetaTF. You can do a contrast over training at each layer and select number of bits to see what the result overall network is. Yeah.
So go to some of the questions from the audience. First question we saw was if you have any benchmarks running something like a speaker ID, basically voice detection or wave to text benchmarks.
Yeah, so I think we have done the same keyword spotting, and we try to match because we have on-chip learning, what we do is once you're speaking into a mic and voice, its MFCC component will be slightly different, and we can label it. So I think if there's some demos, I don't have it here in the presentation, but on a website you can see speaker identification and speaker that this keyword spotting and speaker can be matched. And we have similarly on a facial detection, you can actually just take 3 or 4 face. I mean, you can actually stand in front of a camera and label your face, and it will learn that face features. And actually on the device, you can add with just one shot all of those things. Yeah.
Yeah. Your IP is configurable. How many of the processor cores would be required for keyword spotting?
For the voice, we only need about, there are 2 modes we can optimize it, 7 NPUs or 5 NPU, depending on network that you do. So what we do is, after you take the network and convert it to MetaTF software, it will tell you, it will analyze the network and tell you at each layer how many NPUs are required. And then if you have a 20 node, then it will allow, like a mobile net V1.5 fits everything into about 50 nodes, and you can run it completely on the device. And once, if everything fits on the device, you can run something in the pipeline mode. That means our data converter can be generating spice for the first frame, send it to the first layer. Now the first layer sends data to the next layer. Now it's free, so you can run in pipeline mode and get a better performance. Of course, then you're running a lot more NPUs, so power will be slightly higher, but you can get a better performance. Mm-hmm. So how many processing units are required? It depends on network architecture, weights at each layer, and we analyze all of that information comes out from the software. Before you go to the hardware, you can do MetaTF complete simulation. It will tell you what performance you'll get, how much power will be, how many NPUs are required, will it fit? And that's exactly what we use for people who want to embed the IP into the SoC. They can say, okay, if I license a 4-node IP, this is the die size, this is speed I'll run it at, and now I can do all of this class of networks on that hardware. Or we use it multiple times if the hardware is less. So it's quite configurable from that perspective.
And so is there production RTL is available for licensing now?
Yes, we have already licensed it to one company. They are actually putting it into their microcontroller, and there are other licenses that we are doing. Production IP has been available, with, and now we have a production chip also, same RTL, and the improved version of that is already available in the chip.
We have another question on your digit recognition demo. Was there any optimization done on the accuracy versus energy consumption for that?
Yeah, so yeah, you can use like on the CNN part, you saw that I showed you 95% accuracy. That was off the bat what you saw. But you can spend more time, use our techniques to improve it further, take more samples out of it. Or even on a native SNN, we got an 89% accuracy. If you take more samples and train it for longer, you could improve it. So it's all, it's possible to do that. But it really depends on your application, what you're trying to do and what your data set is. But all of those techniques are available. Yes.
Well, I'm afraid we're out of time, but you'll be doing a breakout session later on today, I think?
Yes, we are.
So we have a few more questions, but so I'd like the attendees to talk to you more later on in the breakouts.
Definitely, yeah.
Thank you, Anil.
We'll come there and we'll see you there. Yeah, thanks.
Okay.